So we're going to change our schedule, and instead of doing chapter 9 and then 13, we're going to do 13 first. Okay? That's because 13 involves carbonyl chemistry, and carbonyls are going to be the most important thing for anybody transferring into biochemistry. Okay? That makes up probably 90% of the reactions that you would ever see in biochem. Okay? So we want to focus a little bit more on the carbonyl chemistry because it's a little bit more relevant to you. And then we'll talk about the chapter 9, which is aromatic structures, in probably the last week. Okay, so we'll hold off on just 1 to 2 lectures with those. Okay? So because this section was also crammed in at the end of last semester, I don't have the nicest slides for it, which means I also don't have the nicest sequence of homework set up for it yet either. Okay? So nomenclature for sure you'll end up seeing. That's what we're going to spend most of our time talking about today. We're going to look a little bit at synthesis for reactions and then reactivity. Okay? The synthesis of carbonyls you guys have actually already seen. I don't think we're going to talk about any more. Okay? Other options to synthesize them. We're just going to focus on the ones we already have. And then we'll look at reactivity. At this point, it's going to be largely based off of the lecture slides that we'll be going through, okay, as far as what things you could expect on the exam. I will try and get some more questions posted this weekend from the textbook, so you've got some problems to actually work with that will hopefully target more of the material. Okay. I've got chapter 9 up there as well, just in case you want to get jump started on chapter 9 homework as well. Okay. I don't want to quite do that yet. Shit. Okay, the first thing I actually want to do before we do nomenclature is look to see what a carbonyl is. Okay, a carbonyl is ultimately just the carbon-oxygen double bond. Okay. It's got a lot of interesting chemistry. It's not quite as bad as alcohols as far as the reactivity goes, but there's a lot of different things that apply with carbonyls that make it a little bit more dangerous to worry about as far as trying to predict different reactions. Okay? So when you see the carbonyl, what chemistry jumps out at you? What do you see? Lone pairs on the oxygen, which would suggest... Okay, I heard a base. Okay, so we're looking at an electron source or an electron donor. Let's go stick with the standard terms we've been using. So we could look at it as a Bronsted-Lowry base. What else? If we've got lone pairs, what other species are electron donors? What's that? We've got nucleophiles. And if you're writing these, I'm about to cross it out, just so you know. And the last one, also got a Lewis base. Why would we expect it to not act very well as a nucleophile or a Lewis base? Oxygen's happy with 2 bonds. Okay, so having it react and add a hydrogen does increase the bonds. It does go positive, but we can take a hydrogen on and off relatively quickly. So that's one of the things that's going to become increasingly frustrating with carbonyl chemistry. So we get a lot of acid-base chemistry. We pretty much do it whenever we feel like to make it work better. Okay, so the acid-base stuff is something that's relatively easy to work with. But if we added, say, another atom, like a carbon atom, okay, we're now making another bond that takes away from oxygen stability, and it's now also a stronger bond, so it's not the easiest thing to do. Okay? So having that oxygen act as a nucleophile or a Lewis base is a bit tricky. Okay? So those are not going to be particularly likely. Okay? What other stuff do we see in there? Okay, we see the pi bond. What's special about the pi bond? What could our pi bond do? If we compared it, say, to An alkene. What reactivity does an alkene have? It's got that pi bond as well. What chemistry is associated with an alkene? It all flipped to the exam. Okay, it could act as a base, particularly a Bronsted base because of the electrons. What else could it act as? Source of electrons. Source of electrons. We could see it act as a Lewis base, potentially a nucleophile. Okay. If we go through and try and apply that back to our pi bond, okay, do all of those match as easily? Okay, why not? When we look at the alkene, where's that pi bond located? Between carbons, same atom. When we look at the carbonyl, where's the pi bond located? Between atoms again, but between different atoms. So is that pi bond equally centered now between them? No. Where does it spend most of its time? On the oxygen. So when we evaluate our carbonyl reactivity, we can pretend that pi bond is ultimately part of our oxygen reactivity. Okay? So we're looking at that oxygen and ultimately the pi bond being responsible for our carbonyl acting as a Bronsted base. Okay? Is that everything in our carbonyl then? No? What else is left? We've got the carbon. Okay? What's the issue with our carbon now? It's partially positive. If we went back to the alkene, though, we wouldn't circle and identify that carbon as particularly partially positive. Why is that a bad assessment to make in the alkene? There's no difference in electronegativity. When we move to the carbonyl, the oxygen changes the chemistry of that double bond. And now that carbon becomes partially positive, which means that carbon can act as an electrophile and there it was, a Lewis base. No.
Lewis acid.
Sorry. You were right on the Lewis part. I was wrong on the base part. There we go. Acid. Okay. Remember, the base would donate electrons. The acid needs to accept electrons. Okay. So when we look at a carbonyl, we get a reasonable amount of chemistry jumping out of it. Primarily, we're looking at our oxygen in the carbonyl acting as a Bronsted base, and our carbon of the carbonyl acting as an electrophile. Okay, so those are our two primary sections for reactivity. Okay. However, or not however, I guess additionally here, we can add a little bit more information to this because we can quickly alter the structure, and instead of it being just a carbon-oxygen double bond, I could go through and say that what that carbon is attached to happens to be carbons. Or we could change it where that carbon is attached to carbon and a hydrogen. Okay. Does that change the chemistry of that central carbon? Should it change the chemistry of the oxygen much? Probably not. We aren't changing what the oxygen is attached to. It's still doubly bound to a carbon. Does it change the chemistry of that carbon? Good. Why does it change the chemistry? Carbon versus hydrogen. Our carbon atom is bigger than hydrogen, which is ultimately going to change how our now green carbon, our electrophilic carbon, can react with other species. Okay? Which carbon do you think would be more accessible? Right side or left side? Right side. Okay? Because we've got a hydrogen versus a carbon blocking it. So this carbonyl we might predict to be more reactive than this one. Okay? It's different enough in reactivity that instead of calling it a carbonyl, we want to come up with a new functional group name. What are the functional group names for these two? We've got a ketone. It's an E. And an aldehyde. Okay. Do we have to stick with carbons and hydrogens attached to that carbon? What if I changed it to, how about an oxygen? That's what I was fishing for, but do we have a carboxylic acid yet? As soon as we add the hydrogen, now it's a carboxylic acid. What if we had now it's not a carboxylic acid anymore. This is one that I haven't told you to memorize because we aren't going to deal with it much. We have an ester. Okay, and this one was our carboxylic acid. Okay. What happens if instead of, just make this super crowded, why not? Instead of an oxygen, I make it a nitrogen. Anybody know what that functional group is? The amine would be the NH2, but when we put the NH2 next to the carbonyl, changes the chemistry and we get an amide. That one's of particular interest because we could go through and instead of that being NH2, if I put a carbon out there, oops, I wanted that to be a hydrogen. Now the bond between the amine and the nitrogen, or sorry, the amine and the carbonyl, ends up carrying a slightly different name, particularly if we shift into the biochemistry context. What's the bond between individual amino acids and a protein? What's that? Okay. So our carbonyl chemistry, just by changing the individual atoms around it, we change the different functional groups, and ultimately here's the big reason why our carbonyl chemistry becomes important. That bond is made and broken every day in everybody's body billions of times over. Okay? So you need to be able to understand why it's there, why does it exist, how do we make it, that kind of fun stuff. Okay? So it's one of the reasons we're going to evaluate carbonyls. We're going to stick to the aldehydes and ketones as far as nomenclature goes and as far as sort of reactivity. Okay? We'll discuss sort of in a little bit. Okay? So, questions about identifying functional groups? Any of that? Okay, so what we'll go ahead and do now is go back to our nomenclature. So we talked about two new functional groups, our aldehyde and our ketone. Might as well draw an example aldehyde for each of these. So our aldehyde is the carbonyl, where our carbonyl carbon, which I now actually have implied, I'll circle it in green, has a carbon and a hydrogen attached to it. As soon as we've got that hydrogen attached, we now have an aldehyde. Okay? As far as priority goes, these start to push quite high in the priority list. Okay? They're not quite as high as our carboxylic acids, but they are now higher than our alcohols and amines. Okay? So when we go through, we're going to treat them kind of similar to how we would treat alcohols. So we'll identify our longest carbon chain again that contains the carbonyl. It's not going to be necessarily at the beginning or end. That's a lie with the aldehyde. Where's the aldehyde going to be? Always at the beginning, okay, unless we have an acid in there. Okay, why does it have to be at the beginning? That carbon for our aldehyde functional group can only continue one direction. Okay? Assuming we don't have any other functional groups like the ester or the acid, aldehydes are our highest priority, which means carbon number 1 is going to start right where the aldehyde is. Okay? So we'll go through and start numbering from that aldehyde, whichever direction we need to. The big ending change that we're going to do is instead of, I left off the E's. Instead of the E ending for either alkene, ine, or ane, we'll substitute that out for the AL ending, okay, for al or aldehyde. Okay? Sometimes you'll see people incorporate aldehydes into the name. That's more of a common name approach. We'll stick with the IUPAC rules for the most part. Okay. We don't need to specify the number in the case of the aldehydes because it's always at position 1. Okay, we can't change that. We can then go through and name the substituents, same rules as before, number, where they're located, and put the whole name together. Okay? Kind of makes sense? Yes, I do have examples. Okay, so let's take a look at ketones. We'll draw out a general ketone structure. Okay, so our ketone has the carbonyl with carbons on either side of it. Okay, it's a little bit lower in priority than our aldehydes. Okay, so we'll go through and find the longest carbon chain that contains the carbonyl. Okay, so just like with alcohols, it doesn't have to be at the beginning or the end of our carbon chain, and in fact, it will have to be in the middle. Okay, because we've got carbons coming off the other end. Okay, in our IUPAC way of naming. Okay, so in the example that I've got quickly drawn there, we would identify those 3 carbons as our main chain. Okay, we could go through with our longest chain being 3 carbons. 3 carbons gives us what? Prop. Other than the carbonyl, do we have any other functional groups? What? Alkanes, so we'll go with propane. We'll change the E ending in our propane to account for the ketone functional group, and we get propanone. Okay. We should specify with the smallest number possible where that carbonyl is located. In this case, it would be located at position 2, so we could call it 2-propanone. Okay. We would then also go through and name the rest of our substituents, just as we had before, if we needed. Okay. Do we need to specify the 2 here? So it's not always going to start at the central one, but with 3 carbons and it being a ketone, the carbonyl has to be in the middle. There is no other option. So we could drop the 2 in this case. If we made it butanone, though, if we added 1 more carbon, do we have to specify the number then? Yes. Well, actually, still not no. Still not no. Let me get that other carbon in there. We still don't have to specify it. Why? 2 or 3, but what's the difference between position 2 and 3? Just a question of which way you counted. Okay? So even with this structure, we don't even have to specify where the butanone or where our ketone is. So we'd have to add 1 more carbon. Okay. Now once we're up to pentanone, we absolutely must specify where the ketone's located. Okay? Because it could be at position 2 or position 3. Those generate different structures. Okay? Make sense? Okay. Wrong button. So let's try and work through some examples. A couple of these I'm going to eliminate right off the bat. I just didn't get time to cross them out yet. Both of these, I'm sure none of the others are in there. Both of those names are coming based on having done Chapter 9 already. Okay? So if you see anything with benzo or phenyl in it, you can ignore doing those nomenclature problems because those assume that you did Chapter 9. It's kind of difficult to do the nomenclature of those functional groups if you've never seen them before. Okay? So let's attempt to do, what the heck? That first one. Oh. Where should we start with the first one? Probably a good idea would be to underline the important part. I personally would do the cyclohex first as an underlining, which would give me what structure? A 6-membered ring. Okay. Next piece of information that I would highlight is different. Whoops. The AN ending in there. What does that AN mean? It's all single bonds. Okay, so I've accounted for that. Next piece of information. I would probably go to the ketone. So the ONE ending means I've got a ketone. Where should I put that ketone? At this point, it doesn't matter. I can put it wherever I want because I haven't specified anything else. Okay. I then have yeah, I know what happened here. Yeah, we'll talk about that in a second. We could highlight the 2, but we'll come back to that, like I said. It's a copy-paste mistake. We've got a methyl located at position 3. I don't want to do this. Ignore the 2. Let's just cross that out. We'll talk about why it's an issue in a second. Okay, or where it's coming from ultimately. Where's position 3? Where's position 1? Where the carbonyl is, so there's position 1. I prefer clockwise, so we'll go 1, 2, 3, and we could add our methyl. And we now have 3-methyl cyclohexanone. Okay? Questions about that? Okay, we'll come back to the 2 in just a second here. In fact, we can do that right now. Yes?
So before the carbonyl was on the second carbon, but when it becomes a ring, like when we were drawing it before?
So on a ring, remember your functional group, your primary functional group is always at position 1. Yep. So when we looked at a straight chain, the ketone has to be in the middle. It's going to have some number somewhere in the middle. Good question. Other questions on that one? Okay. I'm going to erase that, which I'll probably end up regretting here. And we can move on to the next one. So, where do we start with the next one? Same idea, cyclohex. This time, though, it's not an ane. We've got an ene. And in the one, draw out our cyclohexane, our cyclohex. Okay, which takes priority, the one or the ene? The one is our highest priority. So we'll draw the ketone. Where's the ene? At position 2. Okay? When we go through a number, our ketone is again, because it's the highest priority group, starting at position 1 on the ring. 2, 3. At position 2, we have the beginnings of a double bond. Where does that double bond run to? 2 to 3 or 2 to 1? Why not 2 to 1? And then we would have said it started at 1. Exactly right. Okay, so we pick where it starts. Okay? Last part of this, the methyl at position 3, we have the methyl. Good thing we went through and numbered our rings so we know where everything's located. We can now add the methyl at position 3. Okay? So where did the 2 come from in the first part? Copy, paste. I did probably the ene first. The 2 was a carryover from the cyclohexene. Should have deleted it, and I just didn't delete it from the name. Okay? Does that make sense with these 2? Okay. We will go through and do one more. We'll do the hydroxybute now. Again, where should we start? What's that? I would start personally at the bute. Where would you start next? Okay, we could identify the hydroxy as another piece. What other stuff could we identify in here? We've got the ane and the al or al. So to draw it out, I would personally go with the bute first, calling that number 1, 2, that's 3, right? 4. Yeah. So we've got our bute. Ane standing for all single bonds, so we don't have to worry about that. Okay. Al, I do third. Where do I put the aldehyde? The left or the right side of the structure? Does it matter? No. Okay. Our carbonyl, as far as our aldehyde goes, can go in any position. Okay. But it's always good to put it on the right side because then you feel more correct. Right? Yeah. Thanks. Then we can go through and add our hydroxy. What does hydroxy refer to? Hydroxy is an alcohol, an OH. Where is that position? Position 4. Even if you think you can count, which I should rephrase that because that didn't come out right. I know you can count, but it's easy to make mistakes. Go through and put the numbers down. Okay? So our aldehyde is our position 1. We've got 1, 2, 3, 4. We can now add our alcohol at position 4. And we've got our 4-hydroxy-butanol. Okay? Makes sense? How many of you cut up the individual name on like this on the exam? Went through and said, this is a part that I should analyze, this is a part I should analyze. Okay. How many of you got the nomenclature 100% perfect? Okay. If you aren't getting it perfect, you should be specifying all this extra information. It allows you to make sure that you've accounted for each of those individual steps. Okay. Otherwise, you're very likely to miss something. Okay? So please go through, break it down each time, as tedious as it may be. Worst case, you've at least got it broken down to the point where I can look at it and say, oh, you attempted to do some work, I can give you points for that. But if you go through and draw it out without breaking it into those individual pieces, and you draw it out wrong, I can't give you any points. Does that make sense? Okay? So try and use the time you've got as wisely as you can. What's that? This last one, I would need to review. I think I'm going to be right on it, but I'm not positive on it. I will not test you on this last one. Absolutely not. Okay. I'm pretty sure it shows up in the nomenclature in the textbook. Okay. So let's try and break it down as best we can and kind of come up with a guess for the structure together. Where do you want to start with this? Good. I would agree. Okay. And in fact, that even ends with the ane, so I'd go through and draw out my cyclohexane. What other pieces do we have? Okay. Got something that looks like carb that seems a bit weird. And for sure we have aldehyde. Okay. What else do we have? We've got the hydroxy. So at some point we've got an aldehyde, at another point we've got a hydroxy, and we've got carb, which we've never heard of. Okay? So let's try and piece this together. Which of those is the highest priority? Aldehyde. Where should the aldehyde go? Position 1. Where's position 1? Okay? To make it an aldehyde, what do I need? I need a carbonyl, right? And is that physically possible? Can I put an aldehyde on a ring? No. So if somehow the aldehyde is going to be a part of this, we're going to have it come off of the ring. What's the carb referring to? That extra carbon. Okay? Where's position 1 on our cyclohexane? Where our carbaldehyde is. Let's go with a different color. There's position 1. We can then go through 2, 3, 4, 5, 6, and at position 4 we have hydroxy. So for a name that looked brutally painful, wasn't actually that bad to put together. Okay? So you might see the carbaldehyde show up in the nomenclature. All we're pretty much saying is that somebody decided that we couldn't count out appropriately the longest carbon chain. Okay? We can't start counting from that aldehyde and go through and say 1, 2, 3, 4. Doesn't work because it's not a continuous chain. Okay? That ends up doubling back on itself. It's better referred to as the ring, so we have to number or change our nomenclature accordingly. Okay? Make sense? Okay. I do want to add one more. I'm going to quickly attempt to make it up, and hopefully it won't be terribly bad. What happens if we have a ketone and an aldehyde? Or, for instance, a ketone, aldehyde, or acid involved in it? So what we'll do is pick an example where we have a ketone and aldehyde. Okay, so let's draw one out here. We can do our first one from structure to name. Let's say we've got 1, 2, 3, 4, 5, 6. Say we've got this compound. Where's that oxygen? There it is. Okay. I drew it, I swear. So to go through and name, what do we need to do? First thing we should do is circle our longest carbon chain. How many of you circled the longest carbon chain on the exam? Okay. Again, do the simple steps because they can help. Okay, how many carbons are in that longest carbon chain? I get 7. Okay, you wouldn't expect to see 7 carbons on the test because, well, I told you we'll keep it at 6. So I'll tell you we're looking at hept for 7 carbons. Do we have a carbon functional group? Are anes, ynes, or enes? It's all just single bonds within the carbon, so we can change that to hept. Heptane. What about the ending? Okay, do we have a carboxylic acid? No, it's an aldehyde and a ketone. Which one has higher priority? The aldehyde. So what's the ending of our name? We'll change that to the al. Okay. We now need to go through and specify where all of our functional groups are. Should we add the one telling where the aldehyde's located? We don't need to. It's not going to hurt if we do, but we could. So why not? What other functional groups do we have? We have the ketone as part of our chain. Where's that ketone located? Position 4. I have a ketone. But so far we've only talked about naming the ketones based on the ending, their highest priority. Well, we can't do it at its highest priority. So what we'll do is shift to our parentheses. If it's a substituent on something with a higher priority chain, we'll use that parentheses substitution. So we will call this 4-oxo-1-heptanal. Yes. So how would you tell the difference in a name between an aldehyde and a ketone? One's going to be at position 1. The other one will be somewhere else within the chain. Okay, fine. I'll go through and draw it.
I'm just curious.
You got. There's enough. Well, I'm not saying it's a bad question. 1, 2, 3, 4, 5, 6. Let's put on our aldehyde, ketone. That looks pretty ugly. Let me try that again. So, longest carbon chain. Six carbons, so we're looking at hex. What's our highest priority functional group? The oic acid. Sorry, there's a space in there. That's not a very good looking space. Let me try that again. All right, what other functional groups do we have? And our aldehyde. How do we go through and name these? So they're both going to be oxos, located where? Whoops. We have a 4. Ooh, this is interesting.
Wait, would you separate them then? Like have 4 oxos, 6 oxos?
That's what I was about to do. But I'm not sure, in all honesty.
In other words, they won't be on the test.
True.
Yeah, would you say?
I would venture a guess at dioxo.
But then
But you wouldn't know if you were talking about aldehyde or...
Do you need to?
no.
Because you don't get out.
If we go back the other direction, 6 carbons. There's our 6 carbons. We can add the ic acid. There's our acid. At position 4 and 6, I have an oxo. What's an oxo? Carbon-oxygen double bond. At position 4, there's my carbon-oxygen double bond. At position 6, there's my carbon-oxygen double bond.
It would be at the end.
To be given that name, aldehyde, and would you be able to draw out that looking by that?
Yeah.
Yeah.
By that hydrogen, you just know the hydrogen.
So we can imply the hydrogens. Okay? So sometimes you'll see that drawn out where you don't see the hydrogen there. Why can we imply that hydrogen? Because it's bound to the carbon. We're allowed to imply hydrogens to a carbon. So you could see it drawn out just like that. Why do I add the hydrogen? Because that looks really naked to me. That's all it is. So I like to add that hydrogen so that I can see it. Okay. Regardless, the oxo has to show up at position 6. I need the double bonded oxygen. Whatever I've got to do to put it there, that's what I'll do. Just like when we did the ic acid. Whatever I have to do to this carbon to get the acid onto it, that's what I'm going to do. Okay? So given the name, would you be able to specify right away that it was an aldehyde? Probably not. Okay? You would probably have to draw out the structure to see that it had an aldehyde in it. Okay? Does that answer your question? I don't want to go into that, but yes. Other questions on that? There were definitely a lot of people chiming in, so was there other pieces of information people wanted to add to that? Okay. We'll talk about the one last thing that you were mentioning there, Becky. Would you be able to tell that it's an aldehyde? Hex means 6. If you have an oxo at position 6, that's the end of the chain. It has to be an aldehyde. Okay? So you can either kind of shortcut it by applying the rules of your nomenclature a little bit, or you would have to go through and just draw out the whole structure. Yes. I think you could go oxo and then an al. Maybe, no, you go dial. You guys want to see a aldehyde on each end of a structure? I don't know. It's way too early for me to think about what's showing up on the next test. So let's go ahead and take a look at this structure. What do we have? Longest carbon chain. Yeah, I'm erasing. So we've got pentan. Now what do we do? What's our functional group of highest priority? It's an aldehyde, so we could take it to just pentanal, but I have another aldehyde, so we could change it to okay. Do we need the numbers? No, because the aldehydes are by definition going to be at the ends. But again, that's not going to be wrong. Okay? Other questions with these? You're testing my limits of nomenclature. Okay. I'm kind of trying to drag my feet because I know the next part's not going to be particularly fun. So when we look at chapter 13 with our carbonyl chemistry, we've got, the nomenclature of our ketones and aldehydes. So this is ultimately kind of just a review of everything that you're responsible for. You've got your ketones and aldehydes. You're responsible for the general reactivity. Okay, so when you look at a carbonyl, what did we say was our general reactivity? You all got beautiful notes, right? You can tell me what the reactivity was for a carbonyl? What's a base in the carbonyl? The oxygen should work as a Bronsted base. What else can you tell me? The carbon acts well as a Lewis acid. Okay. The next part is going to come down to looking at the reactivity of our carbonyls, and this is where tend to lose a lot of people. And people get mad at me. Okay? It's just carbonyl chemistry. It involves lots of acid-base reactions. So when we go through these, you have to go through it kind of stepwise, slowly evaluate each step as we move, and ask questions if you've got problems with it. Okay? For the first one, our carbon Grignard. So if we come in with a nucleophile that's a carbon, they get special names. They get called Grignard reagents. Any ideas why they might get a special name? Grignard discovered it, but just because you discover it doesn't always mean you get your name attached to it. What's a nucleophile? How would you describe a nucleophile to me, or define it? So something that's negatively charged, which means an electron donor. Right? How often do we see carbon with a negative charge? Doesn't really happen. Okay? We've seen alkenes react, okay, where they give up their electrons, but that's not really the carbon, that's the pi bond reacting. Okay? And the pi bond just happens to sit on one of those carbons or another. Okay? So to generate a nucleophilic carbon is not particularly easy. Okay? So one of the biggest reasons why it became a named reaction, we named it after Otto von Grignard. I think that's actually right. I might be wrong, but okay. So he went through and happened to discover that particular carbon compounds reacted oddly when mixed with metal, and in that process we generated a carbon nucleophile. Okay, so what we're going to do is look at the Grignard reagent, so making the carbon as a nucleophile and then reacting it with carbonyls and seeing what the individual results are from each of those. Okay? Next part is looking at nitrogens as nucleophiles. The primary concern or the result of nitrogens acting as nucleophiles is the formation of an imine, and that can change different terms. Again, you're not responsible for knowing that functional group, just realize that that's a term that's going to pop up. Okay? The next big nucleophile would be oxygen. Okay? Oxygens can work as a nucleophile, and it generates two new pseudo-functional groups. Again, these ones you're going to be responsible for being able to identify: acetals and hemiacetals. Okay, what does hemi mean? Half. So what do you think a hemiacetal is? It's halfway on the way to becoming an acetal. Okay? So we'll evaluate each of these functional groups or each of these reactions, starting with our carbon acting as a nucleophile. Okay. Like I said, don't really have a lot of these prepared. So there's going to be a lot of drawing at this point. Okay. So to get carbon or a carbonyl reacting with a Grignard, so what we're going to do is first just show an example of a carbonyl reacting with one. So let's pick, in this case it'll be acetone, okay, or propanone, because we just got 3 carbons reacting with the Grignard reagent, where we get CH3, and that, oh man, valiant attempt. And that CH3 will be negatively charged. Okay. What would we expect to happen when we mix these two? Oxygen wants the what? What electrons? The lone pair on the carbon? So what you're suggesting is this? Okay. How many electrons are around the oxygen right now? It's got 8. So if we show that arrow as we've got it, we're saying we're bringing 2 more in to share with it. So how many electrons would it have around it? 10, which would be too many electrons, so we'd have to move some electrons away from it. What electrons would we have to move away? We could move the pi bond back towards the carbon. Don't draw this. Okay. What's the problem with that? Oxygen's more electronegative than carbon. So if we take a look at this arrow, sorry, I should pick a different color here. If we look at that arrow, we're taking electrons away from an oxygen, okay, and putting them on a carbon. That's really not a good thing to do. Okay? So, good idea. So we start and we fire it up. Okay? And it turns out that that didn't quite work. Okay? What did we say was our reactivity for our carbonyl? The oxygen acted as a base, and the carbon acted as a Lewis acid. So a Bronsted-Lowry base would react with what kind of a species? Acids, the definition of an acid. Proton donor is the definition of our acid. What charge is a proton? Positive. Would we expect our oxygen that acts as a base to react with a negative charge? No. Okay? So the idea is if you keep going back to those definitions, and I know it's painful because you have to keep slowing down and switching back to those reactions to kind of evaluate each of these steps. Okay? So you picked a good option. Oxygen was a possibility. That's definitely where our reactivity is. It's in that carbonyl. But the oxygen didn't work for us. So where should we try now? Let's have it attack the carbon. Why would it shift to the carbon? That carbon is partially positive because the oxygen's taking electrons away from it due to electronegativity. So to stabilize that partial positive, I want to give it the electrons from our CH3. Make sense? Okay. How many bonds would that carbon then have? Too many. So do I have a weak polar bond? Pi bond's the easiest bond to move, so we will shuttle those electrons up to that oxygen. Okay? At that point, I haven't broken any octet rules. Nothing's completely unsatisfied. We can now go through and see what our product is. Let's go ahead and call this red. Our CH3 shared electrons, so we've now formed that bond. What happened to the bonds up to the oxygen? I broke one of them. So tempting to color code this. So oxygen still has the two lone pairs that it started with, but now it has two more electrons. So it's now negatively charged. Is this a favorable reaction? Okay. What charge do we have on the reactant side? Negative. What charge do we have on the product side? Negative. So they're both negative, so that doesn't really give us any kind of balance. Where is the negative on our reactant side? Carbon. Where is it on the product side? Which atom can hold the negative charge better? Oxygen. Does it make sense to translate to our products? Yes. We're stabilizing that negative charge. We're shuttling it to a position that can better hold the negative charge. Okay? Is that product done reacting now? Okay? As far as our solution goes, there's nothing else to react with. Okay? We just have our propanone and the negative methyl. So there really isn't anything that that negative can now go out and stabilize with. So what ends up happening as far as our reaction goes is it stalls. Okay? And it stops here until we add one more reagent. Okay? You've done this a lot. Trying to think of what experiments you did. I think you've done it at least a few times in lab. You go through, you mix your chemicals, and then you stop the reaction and you end up adding water or something else. What you're doing is usually adding something to quench the reactivity. What's reactive about our oxide? Negative charge on the oxygen. How do I stabilize that negative charge on the oxygen? Positive. What's an easy positive that I could potentially supply? Hydrogen ions. So step 2 of our reaction, you'll usually see it written as H3O+. All we're doing, let me draw that out so we can see the bonds, so I can show the mechanism. So H2O. We will take the electrons from our oxygen, our negatively charged oxygen, share that with our hydrogen. How many bonds would our hydrogen now have? Too many. So we have to break a bond. What's the result? We end up with an alcohol and water. We'll draw the water for balancing sake, but is that important to draw in there?
No.
Not really, because it's not organic. Okay? So when we react to carbonyl with a Grignard reagent, the end result is that we make what functional group? An alcohol. Okay? Can we classify this alcohol? What kind of alcohol did we make? There it was. So we start with a ketone plus a Grignard reagent, followed by step 2, H3O+. We end up with a tertiary. Oh, sorry. Well, that didn't fix it. Let me try that again. We end up with a tertiary alcohol. I'm standing in your view, aren't I? Okay. Make sense? Not so bad, right? Okay. Let's change it slightly now. Instead of this being a ketone, so instead of erasing everything entirely, which you'd probably like me to do because you're probably going to have to rewrite it all anyway, I'm going to go through and change it. It's now not just a ketone. I'm going to make it an aldehyde. How do I make it an aldehyde? Just put a hydrogen there. Does that change the mechanism? Is our Lewis acid carbon still a Lewis acid? Yes. Is our negatively charged carbon still a nucleophile? Yes. So that first step, nothing changes. What changes in the products? One of those methyls needs to be a hydrogen. So we can add that hydrogen. Should add it in black, sorry. So, as far as in that first step, good question. Let me add it in blue. So we're saying that our methyl comes in, attacks, and you're asking why does this not occur? Where do the electrons in that bond go? On to, follow the blue arrows because that's what you wanted to do. They'd go with the hydrogen. So what would my product be? What can you tell me about H negative? Extremely reactive. Why? It's negative and it's as small as we can possibly get. Okay? or hydrogen is a terrible leaving group. Okay? For it to act as an acid, what does it have to leave as? H+, which means that carbon still has too many electrons. Okay? What we have to do is we have to shuttle electrons away from that carbon. Pulling off H+ doesn't get rid of those electrons. If anything, it puts them closer on the carbon. Okay? And that is something that a lot of people would consider doing, trying to shuttle off the hydrogen. Follow the electron flow. Okay? At least initially, go through and balance things until you're confident that you're getting the correct answer each time. So balancing can help you get to this and see, oh, I've got H-. H- is incredibly basic. Okay? Which would mean that is a terrible leaving group. Okay? The other thing that we could go back and evaluate, we'll end it on almost on this. When that comes in, that carbon has too many bonds, right? So what did we say we had to do? We have to break a bond. What bond do we break? So pi bonds are part of it, okay? But there's another case. In a substitution reaction, we don't have a pi bond to break. What bonds do we break? Particular type of sigma bonds. I know, it's a bit of a stretch. Polar. They must be polar bonds. Why? Because that needs to be able to take the electrons with it. So if we now evaluate that carbon-hydrogen bond, is that a polar bond? Carbon to hydrogen. What kind of bond is that? That's covalent. It's not a polar bond. We cannot break that easily. Okay? So yet another reason that it doesn't make sense to attack that hydrogen or have that hydrogen pull electrons off. Okay? We want to talk a little bit more after class. We can do that. I want to end real quickly on evaluating what things changed when we went through and made this an aldehyde versus a ketone. So now when we react our Grignard, we have an aldehyde plus a Grignard gives us what kind of an alcohol? It's secondary. We've got that hydrogen out there, which doesn't count as far as our primary, secondary, tertiary. Okay? So when you react an aldehyde with a Grignard, you end up with a secondary alcohol. If you started with a ketone, you end up with the tertiary alcohol. Okay? We'll review over the aldehyde mechanism once more on Monday, and then we'll also come up with a way to make a primary alcohol, and then we'll look at how we can make the Grignard reagent, so you can see those chemicals.
Would you rather get H plus or H minus in the phase?